Our second speaker is Qianchuan,
Yep.
Talking about Taypsi, static enforcement of privacy policies for policy-agnostic oblivious computation.
Okay. Does this work? Okay. All right. So I'm going to talk about Taypsi, which is a language for oblivious computation. This is joint work with my advisor, Ben, when I was a PhD student. So first, what is oblivious computation? This is a classic example called Yale's millionaires problem. So we have two millionaires, and they want to know who is richer without telling each other how much they have actually earned. So basically, they just want to calculate a Boolean result of a comparison of their income. And that is an example of a general problem called secure multiparty computation, or MPC, which allows multiple parties to jointly compute something without disclosing their sensitive data. And we can achieve that by using some crypto protocols such as Yale's Gabble circuits, and there are other non-crypto solutions like virtualization or secure CPU. And of course, they give you different levels of security guarantees. And there are many applications in these privacy critical domains. And despite all these applications, it remains very challenging for especially non-experts to implement these secure applications. So there are several high-level program languages proposed for tackling different aspects of this programmable MPC problem. So what is the problem we are looking at? What's the angle we are looking at? So consider this example. Let's say we want to build a secure dating app. And one input they need to provide is their personal profiles with sensitive information like age, height, weight, and whatnot. Another input they need to provide is their preferences. I model preferences as ST or abstract syntax tree for some domain-specific language like a predicate language, and I show some sample expression there. Expressions are ASTs. So in this example, we are essentially dealing with non-trivial data, not just integer or Boolean. So for example, profiles are flat compound data type or record type. And preferences are recursive data type. I model them as trees. And with these non-trivial data, we want to run a matching algorithm and basically make a decision of whether these two parties are a good match. However, to implement these applications, we need to solve a few challenges. The first one is we want to support rich recursive structured data, like trees or lists. In particular, we also want to make sure we can hide the structural information. For example, your decision tree might not want to reveal whether it's left-heavy or right-heavy. We also need to avoid leaking private information through how you represent the data in memory and how you build or traverse the data. And the second challenge is that we also need to support complex policies that go beyond just saying this data is private or not. For example, in the healthcare setting, a policy for medical record might be either the personally identifiable information or the medical data is disclosed, but not both. So this is like an either-or policy. And another thing is data structure, like trees, may have multiple policies. I will give some more example later. The last problem is that existing languages usually require programmers to explicitly enforce policies within the program logic. And it gets more complicated when you have complex policies and structured data. This is because you will have to restructure the programs to capture the policies and also make sure the control flow only depends on the public information, which makes the programs harder to read, write, and reason about, makes the policies harder to update and audit, and also makes it harder to support multiple policies. So the bottom line here is basically we want to separate the privacy policies from the application logic. In particular, we want to allow the programmers to write applications independently of the policies and specify and audit the policies independently of the functionality. In other words, we want to have some kind of policy-agnostic approach. And here, I want to allow the programmers to write their functionality as some functional programs with structured data and high-order function and all this good stuff, without thinking of policies, though. And then they can define their policies separately, and somehow we can compose them and derive a secure version. So this is the goal we are trying to reach. And in fact, we have attempted to bridge all these gaps in our previous work. We have introduced something called oblivious algebraic data types, which is a way to encode structured data type and also their privacy policies, which I will briefly talk about next. And we have also proposed runtime semantics called Taypsi semantics, which is a way to enable the separation of privacy policies and program logic. But in the interest of time, I'm not going to mention these semantics. You can read the paper to learn more about it. In this work, we introduced a language called Taypsi, which is extended from the previous work. And it also decouples privacy concerns and the programmatic concerns. But we do it this time by statically enforcing the privacy policies. In particular, we design an algorithm that basically takes a public program and a desired privacy policies, and we can combine them and generate a secure version that respects the policies and also preserve the behavior of the original program. And we ran some experiments. Our results show that this new static enforcement strategy offers significantly better performance compared to the previous approach. Okay. All right. What we'll be doing now is to give you a quick tour through this very simple example about how this language works at a very high level. So this is a list data type with an integer payload. The definition should be very standard as an algebraic data type. And here we have a filter function with a threshold as an argument and also a list of integers. So basically, this function does is basically just like keep all the numbers in the list that's below the threshold and remove the others. By the way, we do support higher order functions. This is just a simplified example. Okay, now we have a data and also a program. To implement a private version of that, we first need to give them some privacy policies. So what is a policy? In this context, a policy specifies what information can be publicly shared, which can be any arbitrary projection of the data because we want to support complex policies. And we call this publicly shared information public view. And then we can encode a policy for structured data as oblivious algebraic data types, or OADT. I'm not going to talk about the details of how this works because it's not very important for this talk. But we defined an OADT called list head something. The head here doesn't mean anything. The syntax is just a visual cue for security stuff. So an OADT is a dependent type, which depends on the public view, which again is the publicly available information that everybody agrees on. And in this case, I choose the maximum length of the list as the public view. So essentially, the policy for this private list is that I want to hide everything except for the maximum length. I can release the maximum length as long as other things are kept secret. And the type body here describes the representation, or you can say the shape, of the private component of the private list. And importantly, this shape is completely determined by the public information, which is the type index. So that the attackers, does the mic working? Okay. So that the attackers cannot infer any private information by looking at how the data is represented. And we also have some oblivious operations to build and manipulate OADTs, but I'm not going to cover those. Okay, here's one example of the previous OADT with the public view 2. So basically, this is a private list with at most 2 elements. Here is one instance of this type. It has exactly 2 elements. And here is a list with only 1 element, and here is an empty list. And a key here is the OADTs will automatically pad this private list with dummy secure values so that all the private lists of this same type of this OADT will have the same representation, or you can say they look the same to the attackers. They are indistinguishable regardless of how many elements they actually have and what exactly these elements are. Okay, and of course, revealing the maximum length is just one policy. You can also choose to just disclose the exact length. By doing so, you hide less information, but also you have more succinct data representation and more efficient computation. So here's some trade-off you need to make. Okay, all right. To enable modular translation, in this work, we extended the previous type system with something called site type. So what is a site type? You can build a site type by putting a site before the OADT, but if you know dependent type, it's really just a fancy name that I gave to this variant of dependent sum type. And here is one instance of this type. I use this pair syntax because dependent sum type is secretly just a fancy pair. So the first component of this pair is the public view, the publicly known information. And the second component is the secure value, the secure component whose type or shape is indexed by the first component. So basically what we do here is we package the private data with the public view, and by doing so, we effectively hide the dependent types from the end users. And with that, let's say we want to implement a private version of this filter function. All you need to do is just to provide a different type signature, which still has to be compatible with the original type, and we have a more precise definition of compatibility in the paper. But in this case, we want to take a private integer for the threshold, and we want to take a private list which discloses the maximum length and return the same OADT. And the implementation of this function is literally just like calling a meta function called lift on this public filter function. And if you want to use a different policy, you just specify different type signature, and that's it. But of course, it's still possible to specify an invisible policy. And in this case, the type checker will just yell at you. In this last example, if you know the exact length of the input list, it's still impossible, or you can say insecure, to reveal the exact length of the resulting filter of the list, because the threshold and also all the elements in the list are still secure. So, okay. Unfortunately, I'm not going to go into details about how this lifting algorithm works, but at a very high level, the lifting algorithm, that lift keyword, translates a normal standard program to a version of a given type signature, or you can say policy, with some types variables, while generating constraints over these variables. And then we solve the constraints, and finally, we instantiate the type variables with the solutions, and then do some massage on the program to make them better. And this process, as you can tell, is very similar to a type inference algorithm. Okay, so the constraints we generate assert the capability of the types and also the relations on the type. For example, one constraint is if the type have certain structures. And I didn't actually mention about structures, but each OADT is optionally equipped with a set of structures with the methods and also the laws they need to obey. In the paper, we have the mathematical definitions of all these structures, but I'm not going to talk about them here, but these structures are key to the translation algorithm. Okay, in terms of constraint solving, most constraints are lowered to formulas in an efficient logic called quantifier-free finite domain theory. For some other constraints, for example, the function call constraints, which resolve the policies of intermediate function calls, they are handled similarly to a fixed point calculation. So essentially, the constraint solving is just the interplay of these two components. All right. Of course, now we introduce some compilation overhead because we need to do some constraint solving, and we use Z3 for solving the quantifier-free finite domain theory. But fortunately, as you can tell from the table here, the compilation overhead is pretty reasonable, and the lifting algorithm is expressive enough to capture all the case studies from our previous work and also some new case studies we added to this work. So in terms of performance, I'm not sure if you can see the text there, but it doesn't really matter. The blue bars means the running time of this new approach relative to the old dynamic approach, and the red line there is the baseline. So the blue bar, the shorter of the bar, the better. And there are some green test cases there. Those are the test cases where the previous approach simply just times out or runs out of memory, but the new approach can finish them in seconds. So the takeaway here is basically this new policy enforcement strategy is exponentially better than the previous one in performance for many applications, but work roughly as well for the rest of them. I will quickly gloss over all the formal guarantees. We have formalized the core calculus, and we have a cool type system, but I didn't have time to talk about it. But we have proved the type soundness property and also a security property called obliviousness, which basically says no private information can be inferred by observing every program state of the execution traces. And we have proved the lifting algorithm always generates secure implementations, and also they always generate correct implementations in the sense of a refinement. So basically what that means is the generated programs preserve the behavior of the original programs. And this refinement is formulated as a step index logical relation. I also show some theorems on the slides, which probably don't make much sense out of context, but I put them there anyway to show you I'm not pulling this claim out of my ass. Okay, and to wrap up, we have this language that supports rich private structured data and complex policy through oblivious algebraic data types. And we have a security type system that makes sure the programs are safe by construction. And we allow the users to easily implement their privacy, secure applications by decoupling the privacy policies from the program logic using this lifting algorithm that statically enforces the privacy policies. And we got theory and also implementation for the type checker and end-to-end compiler for Taypsi that you can play with. And with that, that's pretty much it. Thank you for your attention, and I'm happy to take any questions.
Questions?
It wasn't clear the attacker model. Are you considering timing?
Yes. The timing channel is handled by our security type system. So basically, the formal guarantee we have for the language, the oblivious property, implies a stronger threat model in the sense that not just observing the timing channel, even if you can observe every program state of your program execution, there will not be any information.
All right, so I have following up question then. So because you generate these stars, when you don't have information, you want to create a list of certain size, then you have certain stars, right? Because you might not have the whole information.
Right.
So what is the semantics? When a function hits a star, it still needs to continue computing till the end of the list. And I could imagine that if you are doing a filtering, the way that you compute with a star is in one way. If you do an addition, you need to be constant time in the addition, So because here what you're showing, you have n reduction steps in the semantics, which might not be the same as the timing that you observe in the program. So how you bridge that gap?
In our formal model, the semantics of the language, we basically keep track of every program state, and we make sure if you have like two indistinguishable programs, in the sense that they only differ in their secure values, they will always kind of execute in this like matching style. And every
I get that, but maybe we can chat offline because maybe I can explain.
No, I think I get your point, but in terms of timing channel, it is subsumed by this model. But I guess there might be some like more subtleties that that's in your mind that probably is better to take it offline.
All right, thanks.
All right, so we have to move on to the next speaker, but thank you again.
Okay, thank you.